Hello everyone. We are going to learn today about nearest neighbors methods. Okay, this family of algorithms is quite present in classical machine learning approaches for data science problems, as well not only for unsupervised learning like classification or regression, but also k-nearest neighbors is the seed or is the common ground with the k-means algorithm for clustering. Okay, so it's a very important algorithm, which even though it's not usually the most powerful or the one that achieves the best results, is always good to have it in our tool belt. Okay, and it's great to understand how it works, because for some specific scenarios, okay, we might find that it's useful when we don't want to overcomplicate or we just need a easy heuristic on how to classify. Okay, so let's start with it. So KNN, or well, I'm going to refer to the nearest neighbor methods as KNN, coming from K nearest neighbor. Okay, is an approach for classification or regression, which is instance-based. Okay, what this instance-based approach means. Okay, well, it means that what we are trying to do is to find an instance or an observation, a point, okay, that is the most similar to a new instance, or the instance that or the observation or the point that we want to classify or to predict. Okay, so it is clear we need to find something that is very similar to what we have, and then assign the label or the value that the closest one has to my new point. Okay, but how can we define similarity? What is most similar? How can we put a number to it, or how can we rank a similarity in between observations or in between methods? Okay, well, here's where math comes handy. Okay, because we will be using a distance function. Okay, we will define what's a distance function and all the distance functions that we can use in this problem. Okay, and then once we have measured all the distances in between the point I want to predict or classify and all the points around it, okay, we can then select which one is the most similar one according to the distance. Okay, and if we have more than one point that is in the vicinity, or is that is within the distance that we have assumed that is similar, okay, then we can vote. Okay, we can use a voting method for choosing what's the value. For example, as I mentioned in class the other day, if around my point we have 3 close points in which 2 of them have label let's say green, and 1 of them has label red, okay, if we make a voting majority, the final result would be green, 2 versus 1 red. Okay, so that's how the voting works. So let's dig into the distance concept, because it's really important, not only for KNN but in general for in machine learning. It's used left and right. Okay, so in the end, what we need the distance for is in order to rank which point, in order to rank the points that are surrounding the point I want to classify, the point I want to study. Okay, so let's dig in the math of what's the distance in mathematics. Okay, a distance is nothing but a function that takes 2 points, okay, and then returns as a scalar value that measures how different these 2 points are. Okay, it has several properties, like it must be strictly positive. Okay, the distance in between 2 points can only be 0 if and only if the 2 points are the same. Okay, also the distance doesn't have a sign, meaning that the distance in between point A and B, or point X and Y, is the same as the distance in between Y and X. This is something that we already know, because the distance in between Madrid and Barcelona is the same as the distance in between Barcelona and Madrid. Okay, and also there is another nice property, which is that the distance in between point x and y plus the distance in between y and z, okay, it's always greater or equal than the distance in between x and z. Okay, this is another property of distance function. Okay, so now that we have the math behind the distance function, let's see which distance functions or which distances we can use in our approaches. Okay, as you can see, we are used as having distances that return numbers, like for example kilometers, miles, centimeters, light years, sorry. But there are many other distance functions that provide with other values. Okay, so for example, when we are talking about the measuring distance in numerical variables, okay, we usually use the Euclidean distance. Okay, Euclidean distance is the one that we have always used. In one dimension, it's basically the difference in between the two positions of the points. Okay, when we increase the dimensions, though, we have to use the formula that we all know. Okay, which is, for example, if we are in 2 dimensions here, okay, we have point A and point B. Okay, the distance in between A and B, we can calculate it as the square root of the difference in the positions of x for B and x for A squared plus the difference in the positions for B and A squared as well. Okay, where this is x for A, this is x for B, this is y for A, and y for B. Okay, this is what we have always used in high school, in the university. Okay, but there are other functions that with which we can calculate distance, like the Manhattan distance, Minkowski's distance. Okay, also for when we are talking about points here. Okay, but what if we're talking about vectors? Okay, vectors or arrays. How can we check how similar are two arrays, okay, or two vectors? Well, then we can use the dot product formula in order to extract the cosine similarity or the cosine distance, or we can use the correlation. Okay, and then for other purposes, there are many other distance functions, okay, which are mentioned here, but are not the purpose for this course. Okay, so let's dig a bit more into the difference in between the usual numerical functions for distance, like Euclidean distance and Manhattan distance, plus Minkowski's, and the ones for vectors or arrays. Okay, so Manhattan distance is the distance that we humans use for example, walking in a street. Okay, if we are walking in a street and we need to walk from this corner in a block to this corner in the same block, we cannot go through the building. Okay, we cannot do that. We should be breaking walls. Okay, so what we can do, though, is to go walking this street up and then this street right, okay, to get to the point that we want to get to. Okay, but again, the distance, it's not the same. If we are measuring the diagonal here, okay, this would be the Euclidean distance. Okay, whereas if we add up these two pieces of walk in the two different streets, this is the Manhattan distance. Okay, so this is the difference in between these two the usual distances. Okay, then we can use the Minkowski's distance, okay, which is defined up here. Okay, in which distance between x and y equals the sum of the difference in each coordinate, okay, to the pth power, okay, and taken the pth root, okay. So this is the Minkowski's distance. As you can see, Minkowski's distance, okay, depends on this p factor, okay, and if we change this p factor, we will change the behavior of our function, okay. If as you can see, for p equals 2, we get Euclidean distance, okay. It's trivial to see that. This is the Euclidean distance, which corresponds to a Minkowski's distance with p equal to, okay. So now let's dig in the distance for array methods, okay. We already know how to check similarity in between two variables, okay, using a concept called correlation, the Pearson correlation score, which is it tells us how similar are two variables, two lines, two arrays, okay. But also we can use the cosine distance using a property coming from the dot product, okay. If you remember from your time in high school, okay, when we have two vectors, vector A and vector B, okay, these two vectors, when they form an angle, in this case phi, okay, we can calculate the cosine of this angle by using the following formula, which is the dot product of my two vectors divided by the product of their norms or their modules, okay. So with this formula, we can see that if the two vectors are perpendicular, meaning that the angle they form is 90 degrees, okay, we have the cosine of 90 degrees, okay, which is, in my case, it would be the dot product for A and B divided by the product of their norms, okay. So in this case, the distance wouldn't be we cannot, there is no similarity in between them. They are in this case, the distance tells us that they are the most different as they can be, okay. So in our case, when comparing vectors or comparing arrays, when we get a 90-degree position in between them, okay, that tells us that the two vectors are the most different that they can be. On the other hand, when the angle is 0, okay, that means that the two vectors are the same, okay, they are the same vectors, or they lie in the same line, okay. They might have different lengths, okay, but the line in which they lie is the same. So let's take an extra step on when using KNN with or without scaling, okay. If you remember from our previous classes, we learned that for algorithms that depend on distance calculation, okay, scaling the variables is crucial, okay, because otherwise we might find ourselves in a situation like the one you can see here, where on the left hand side we are not scaling the variables, okay, and one of our variables, the one in the x-axis, has a range in between, let's say, 7,000 and 12,000, okay, and the y-axis ranges in between -1 and 6, okay. There is 4 or 5 orders of magnitude of difference, okay. So if we try to use k nearest neighbors, okay, when calculating distances, okay, the distances are going to be, let's say, poisoned by the variable that has the biggest scale, okay. So we shouldn't let the variable with the biggest number win just because the choice of scale, okay. So let's be fair always, okay, when calculating distances, and then we scale each one of the of the features, each one of the variables, so that they range in a similar in between two similar values, okay, and only then we can use our method, okay. As you can see here on the right hand side, once we have scaled, the classification becomes useful, or it's doable at all, okay, because we can see that now we can actually calculate the boundary in between the two areas, okay, for classification. So let's see some examples on using these distances that we mentioned here, the distances that compare arrays, okay, or compare items that are not numbers, okay, or positions. And one of the most used examples for this approach is when dealing with text, okay. In this case, we might be dealing with several documents, which might be several books or several articles, okay. Each one of the articles can be referred as letter A, letter B, letter C, okay. Plus, what we have in each one of the articles, in the end, it's a bunch of words, okay. Articles are made by words that we humans write, okay. So if we calculate the frequency in which each one of the words that exist in all of the documents are present in each one of the documents, which is what we are doing in this table here, okay, we can use something called term frequency inverse document frequency, which is a formula that creates a relation in between how many times each one of the words appear in each one of the documents, okay, and also relates that to how many times how many documents contain that word within all my set of documents, okay. That can give us a probability of a word appearing in each one of the documents, okay. Therefore, we can understand how important the word is to a document in a collection, okay. Another example can be using the cosine distance or cosine similarity, okay, when we are comparing again documents and queries, okay. So as humans know that a lion, a leopard, or a tiger are all of them feline animals, okay, and we know that the three of them are quite similar in between them. But if we are in this situation a dog, okay, the dog word, we know it's not that similar to lion, leopard, and tiger, okay. But how can we measure that in a mathematical way, okay? Then what we can do is to use something which is called word2vec, okay. Word2vec approach converts words into vectors, okay, and once we have vectors, we can calculate similarities using the cosine method, okay. So in the end, cosine similarity can allow us to understand how similar are two documents, how similar are two articles, okay. And in this case, what we are going to do is another example using the same concept, using the cosine for understanding similarity, okay. And we are going to break apart each one of the documents into the terms that they contain, okay. And well, even though this example is we can do it manually, you have the calculation in code down there in the slide, so that you can actually learn how to calculate the similarity between two documents, okay. So this is a very easy way to use something that we have used all of our lives, which is distance, into a world that it has not been easy to use a similarity that was measurable, like for example similarity between documents. So back to k nearest neighbor, okay. And as we mentioned, what we want to understand is for each one of the observations that I have in my data, okay, we want to see if the surrounding points to the one that I want to understand dictate or more or less tell us what's the label that should be assigned to the point I'm studying, okay. we can see that depending on how many neighbors we are measuring around my point, okay, the value assigned to my point will change, okay? And the let's say the motto behind k nearest neighbor is that similar things exist in close proximity, okay? And this is something that we already do ourselves as humans, okay? When, for example, we ask or a friend tells us that they have seen a new movie, okay, and we ask them how was the movie, okay, because what we want to understand is if we would like that movie based on my friend liking that movie, okay. If that person I'm talking to is my friend, chances are we have similar hobbies, we have a similar taste in music, a similar taste in movies, okay. So if we ask one friend about a movie and they say it's good, you should see it, okay, then that's a good proxy of that movie being something we would enjoy, okay. If we keep asking friends around us, okay, we will have a less biased opinion, okay. Plus we will throw in some generalization, because some of our friends, even though they are our friends and they have similar tastes in movies, which is this case, they might say the movie was good, but the soundtrack was not so good, okay. And this way we will add in some negative cases for us liking the movie, okay. In the end, if we ask enough people, we will form an opinion good enough to say we will like it or we will not like it, okay. But this is something that we do on a daily basis, okay, when talking about clothes, movies, food, whatever, a restaurant, a trip that we want to do. And if enough people around us that we trust, that we feel that we are alike, they say that we would enjoy it or that they liked it, okay, then chances are we would like it, okay. So let's put this into math, into the tools that we are going to use, okay, and let's start defining its characteristics, okay. So first of all, k-nearest neighbor is a memory-based approach, okay. This means that the k-nearest neighbor algorithm memorizes every distance to every point that we have in our training data, okay, and then based on that it gives us a prediction for each one of the points, okay. But this is key in when choosing our algorithm. If we have a big enough data set, my algorithm will memorize the whole of it plus all the distance in between each and every point, okay. This is a lot of memory needed to create a prediction, okay. So given a new instance, once we have trained our algorithm in all of our training data, okay, we will find one from the memorized data set that with which we trained it, okay, and then within all those memorized points, okay, we will find, or the algorithm will find, the one that most closely resembles the point that we are trying to predict, okay. So how do we define this how a point closely resembles another? Well, distance, okay, it's distance all the time. Also, another characteristic of KNN method is that KNN method is a lazy method, okay. This means that the actual work of prediction, okay, is not done until a new point is to be predicted, okay. When we are doing the training, okay, we are memorizing, okay, but there is no calculation done. It's just loading all that information in memory. It's only when a new point comes to be predicted when the calculation happens, okay. So it has pros and cons. The pro is that there is way less data pre-processing when we are evaluating the model, okay. But when we are predicting, when we are inferring, when we are creating a classification or a regression, okay, when we are getting which will be the price of tomorrow, or which will be the rating this user will give to this movie, okay, is when it's going to become computationally expensive, okay. So keep that in mind. When training, it's not computationally expensive. When predicting, it is very computationally expensive. Okay, so let's see these two situations in which we have two data sets with points in 2 dimensions. Each point has a label which is A or B, or triangle or circle. Okay. In the left-hand side, we can see that the boundary that separates the two labels can be quite easy to find. Okay, by choosing some diagonal line across that surface, we will be able to separate our classes quite good. Okay. On the other hand, on the right hand side, we can see that the observations are super mixed. Okay, and now the decision boundary will not be as clean as the one we had in the left. Okay, so with nearest neighbor, what we can do is check each individual point that we have there. Okay, and checking all the nearest points around it, we can say, okay, the point that we are trying to predict has 3 triangles around it, 2 circles around it, so we are assigning it a triangle class, okay, or a B class. Okay, that's how KNN works. So we can build our own KNN classifier with this super easy data. Okay, in this case, the algorithm using pseudocode is, first of all, we compute the distance between each 2 points. Okay, each one of these points will be used, and we will calculate the distance in between each 2 points. Okay, a point is defined as the pair of x and y. Okay, so the first row defines a point, the second row defines another point, third row defines another point, and so on. And we will calculate the distance in between first and second, first and third, first and fourth, and so on, until all my points have been calculated their distances. Okay, and now for each one of these distances that we have calculated, okay, we are going to check for each point that we want to predict. Okay, for each one of the new points. Okay, we're going to check, given my point, I'm going to calculate the distance to all of the points around it. Okay, and then what our choice is, the first hyperparameter that we will have to tune when using KNN is how many neighbors around the point that I'm trying to classify I want to keep in mind in order to predict the class. Okay, meaning how many votes I want to let the points around it have. It can be 1, 2, 3, 5, 10, 100, you name it. Okay, this is up to you. The smaller the number, okay, the more overfitting. The higher the number, the more generalization. Okay, so in the end, there is always a trade-off, as it always happens. If we choose a value for k which is very low, we will most probably overfit. On the other hand, if we choose a super high number, like 1,000 neighbors per point, okay, we will not overfit, but we will probably underfit, and we will not have a meaningful response. Okay, so it's the virtue is in the middle. Okay, again, we will be KNN uses Euclidean distance mostly in every situation. You can define other distances if you want within each implementation of the algorithm. Okay, so what we are doing in the end, as I mentioned, is we are calculating distances in between every 2 points. And we can describe that as a matrix, okay, in which the main diagonal contains zeros, and the rest of the points represents distances between points. Okay, so for example, if we have this example here with point A, point B, and point C, okay, we can calculate the distance matrix by saying that, as I mentioned, the main diagonal will be filled with zeros, but each of the remaining positions in the matrix will be filled with the distances. Okay, so in my case, this will be the distance in between A and B, this will be the distance in between A and C, this is the distance in between B and C. Okay, and since remember that we said that distance in between X and Y equals distance in between Y and X, okay, we can use this property of distance to fill the rest of my matrix, okay? Because the distance in between B and C is the same as the distance in between C and B, distance in between B and A, and distance in between C and A. Okay? So now we have a matrix. We have converted a table of points into a matrix of distances. Okay? It's always a square matrix with the main diagonal filled with zeros. Okay? This is what we just did. Okay? And now it's with this matrix when with which we are going to use the actual algorithm of KNN. Okay? So now that we have the distances, okay, let's follow the steps of the algorithm. Okay, so to access the k nearest neighbors of an item I, in this case, we need to select the ith row in the distance matrix, okay, and reorder in increasing order. Okay, so using the same example as we have in the slide, okay, we have A, C, and B, and we have calculated the distances in between each one of the points. Distance in between A and C is 4, distance in between C and B is 3, distance in between A and B is 2. Okay, so now our matrix looks like this. Okay, and now using k equal 1, okay, for the second item in our list. Okay, this means we take the second row, okay, we have a vector which is 2, 0, 3, okay, and then we reorder it in increasing order, which is 0, 2, and 3, okay? And what we are going to do is only return the k first element besides the 0, because 0 is the distance in between the second point and itself. So the first, or the k neighbor with k equals 1 has a distance of 2, okay? So that's all there is in here. This is all that the algorithm does. With more data, with more variables, it's a bigger matrix, but that's it, okay? And this is an implementation made in R. We will be working in Python though, as we will see in this forum, okay? But this is just an example on how to do it in R as well. As I mentioned, as we increase the number of neighbors, the k value, we reduce the overfitting, okay, and we create a more smooth decision boundary in between the two classes, okay, but at the risk of generalizing too much and creating a quite dull, let's say, algorithm, a quite dull model of our reality, okay. This is another example of the same case in which, as we increase the number of neighbors, the k value, we reduce the overfitting. As you can see in the top left corner, it is clearly overfitting because the decision boundary is super close to this, to those, let's say, 6, 7 red points that are within the blue area, okay. And on the other hand, in the bottom right corner, we can see that as we have increased our number of neighbors for making decisions, the decision boundary is way more smooth, okay? It generalizes way better. So how can we use KNN for the two main problems that we find in supervised learning, okay? Well, the first bullet point represents the general approach, okay? Given an object X, find the k most similar object to X, okay? And then, given the property of those k most similar objects, we apply the majority of that property to the point X that we want to classify, okay? But in a more specific for classification purposes. Okay, remember that we will be trying to predict a categorical variable. Okay, classification is predicting labels like red or green, male, female, default, not default. Okay, you already know that. Okay, so for classification purposes, we use KNN in the following way. First of all, we find the class label for each one of the k neighbors that we have around the point that I want to classify. Okay, and then we use a voting or weighted voting approach. Okay, in order to determine the majority. Okay, so for example, if we go back to the tablet, okay, let's say we have this situation in which we have 3 blue points and 1 green point. Okay, so now we want to classify this point here. Okay, well, let me make it less symmetric so that there is actually some fight in between the classes. Okay, and now we want to classify the point X. Okay, so with k equals 1, okay, we check which one is the closest neighbor to my black point here. Okay, let's say is this green one. Okay, so with k equals 1, we have it green. Okay, the prediction of my point is green. Let's increase the complexity. Okay, and now we use 3 closest points. Okay, with 3 closest points, I would say is this one and this one. Okay, so now we have 2 blues and 1 green. If we use a simple majority, that would mean that the decision is blue in this case. Okay, so we can keep doing that, keep increasing the number of neighbors we are taking into account for my prediction. Okay, and then we assign the majority of the labels to my point. Okay, we can do exactly the same for predicting a continuous variable, which is a regression problem. Okay, but in this case, instead of using a majority of labels, a majority of colors, a majority of female versus male, okay, what we can do is to use the average. Okay, so in this scenario in which we have now let's say different properties, like for example, instead of blue and green, now we have a numerical variable that says let's say this has a value, let's say a price. We're predicting a price 5, price 4, price 3. Okay, now in this case, with the same 3 neighbors that we are using, okay, instead of looking for the majority, because there cannot be a majority here, or it's rare that unless they have similar values, what we can take is the average, okay, which is 5 plus 4 plus 3 divided by 3. Okay, and this would be the predicted value that I'm going to assign to my new point. Okay, so we can do this with as many points as we want. Okay, and we will always have a final prediction, be it a class or be it numeric, a continuous variable. Okay, so we can also combine these functions. Okay, we can use what's called the democracy approach. Okay, in which we're not using just the majority. Okay, we can also use like a tiebreaker. Okay, or we can assign different weights according to a specific function we want. For example, we can assign more weight to all those points that are closer to my point, or inverse a weight which is inverse to the distance. In here, you can be as creative as you want, as long as it works for your purpose. Okay. There is something I want to remark here, which is the impact of the value k, of the number of neighbors we are taking into account in our predictions. Okay. In general, as you've seen in this example, when we change the value of k, we change the outcome of the classification, okay, or we change the outcome of the prediction as well. Okay, so what we can do is we can associate a confidence level with our predictions, okay, which can be the percentage of neighbors that are in agreement, okay, and we can have, let's say, a measure of the quality of my predictions, okay, because it's not the same if we, for example, with two classes it's quite easy, but if we are talking about the a situation in which we have, let's say, 100 different labels, okay, and each one of my neighbors is weighing each one of the classes with the similar let's say weight, okay, there is not a clear decision, okay, unless there is a clear majority of decisions on which is the class of that should be assigned to the point, okay. We don't really have a confidence level that we can use to say, okay, this is a good prediction because most of the neighbors were or agreed on the value, okay. So this is something we can do, which is using the number of neighbors that are in agreement as a proxy for the confidence level in my predictions, okay. So if there are strong variations in the results for different choices of k, for different choices of nearest neighbors, okay, this is an indication that usually that the training data is not large enough, okay, because if when changing from k10 to k20 the outcome of the predictions changes dramatically, okay, then you need more data because this shouldn't happen, okay. So this is an example on this voting approach that I just mentioned, okay, and we are going to use the percentage of agreement as a confidence level for us, okay. So we have this this data set with 5 observations, 1 to 5, okay, for IDs 1 to 5, and then there comes a new observation that we want to predict its response, okay. As you can see, the data available is ID, gender, age, salary, okay, and the target is to whether or not they responded, okay, to a specific solicitation when a customer is contacted, okay. So let's use the voting method, okay, without taking into account the confidence of each one of the predictions, okay. So let's focus in this table in the middle, okay, and in the second row, using the Euclidean distance, okay, we can see that using the Euclidean distance we have ordered the IDs from closer to further of my new line, as you can see, which gender female, age 45, and salary 100,000. Okay, so using that sorted list of neighbors, we can start checking the prediction or the value for the response for the target variable according to the number of neighbors that we want. Okay, so we start by 1. Okay, so with k equal 1, okay, we can see that the closest neighbor is the 4th, okay, which responded with yes. Okay, we increase complexity, 2 neighbors now. Okay, then the 2 closest neighbors are 4th, the ID 4 and ID 1. Okay, which that means that the 2 responses are yes and no. Now we have a tie. Okay, then we should define a tie-breaking approach for this type of situations. Okay, but usually this comes already implemented in the algorithm that we will use in scikit-learn, for example. Okay, so as we keep increasing the number of neighbors, we see that we regularly find ourselves in tie situations, that have the same amount of yeses and nos. Therefore, no decision can be made, or can be made easily without breaking a tie artificially. Okay, so now let's switch into using the confidence method. Okay, and now what we are to check is not only the response, which can be yes or no, but also the number of neighbors in agreement with that response. Okay, so for example, now with the same distance, Euclidean distance, in this second table, okay, we can see that the closest one was the 4th one, okay, and it said yes, so we have 100% of agreement or confidence in that decision, okay, in having a yes for the new observation. On the other hand, we keep increasing the number of neighbors. We move to k equals 2, and now we have, remember, a yes and a no. Therefore, the confidence is now 50%. We have one for yes, one for no. Each one of them get 50%. If we keep increasing the number of neighbors, we see that we will not only have a decision, but also we will have a confidence, a percentage of confidence, which we can use to assess the quality of my predictions. Okay, this is what the voting approach is. Why is it useful to understand the quality of my predictions? Okay. So combination functions, when we don't want to use, for example, the majority, okay, we can use a weighted voting, which is not so democratic, okay, because we can assign different weights to different distances, okay. And what we will be doing with this approach is which neighbors' vote counts more towards the final decision, okay. So how can we measure these weights? Well, it's easy. We can measure them based on the distance, okay? As I mentioned, directly or proportional to the distance, we increase the weight, okay? Or inversely proportional to the distance, we increase the weight, okay? Or the weighted sum of each class, okay? Or we can also define a artificial heuristic that we like or that we think that can be good, okay? And this is usually used when you have enough domain knowledge that you can actually put that domain knowledge into choosing which of the neighbors will have a better understanding of the new instance that we want to predict. Okay. The advantage of this approach is that it introduces enough variation to break the ties. Okay, without increasing the complexity leading to overfitting, okay? And also it helps us distinguish between two competing neighbors, okay? When we have two neighbors that are competing, there is a tie that needs to be broken, okay? So we break that tie using this weighted voting, okay? So another approach that another use case for KNN is, as I mentioned, we can use it for supervised learning, classification or regression, but also we can use it for something called collaborative filtering, okay? Or this is segmentation or clustering, okay? It's a similar concept to those, okay? And this is, for example, something very similar to what Netflix does when recommends us a movie, or when Amazon recommends a product when we are browsing, okay? So this is based on what people like us have chosen to see, to consume, and the system thinks that since we are more or less alike to those people, then whatever they liked, we will like as well, okay? So that's the concept behind it. Let's do it manually because it's really simple to do it. Okay, we can encode it then with Python to create an algorithm. Okay, but what we are dealing here is we have 5 people. Okay, that have watched some movies. Okay, Sally, Bob, Chris, and Lynn have watched Star Wars, Jurassic Park, Terminator 2, and Independence Day. Okay, and they assign a specific rating to each one of the movies. Okay. But now it comes a new user called Karen that she has watched Star Wars, Jurassic Park, and Terminator 2, but she hasn't watched Independence Day, okay? So the question here is, will Karen like Independence Day given that she liked Star Wars, she more or less liked Jurassic Park, and she didn't like that much Terminator 2? That's the question that we want to solve here. And we can use KNN for collaborative filtering, okay? So let's start doing the same thing that we are doing all the time, calculating distances in between all the points that we have, okay? In my case, we are going to calculate distances in between people, okay? And the subject that we want to analyze, which is Karen, okay? How can we measure the similarity in between Karen and Lynn, or Karen and Chris, Karen and Bob, Karen and Sally. Well, given that the 5 of them have watched Star Wars, Jurassic Park, and Terminator 2, okay, we can use as similarity or as distance the average rating that they used for the movies, for the 3 movies, Star Wars, Jurassic Park, and Terminator 2, okay? So if we focus in this, for example, in the Euclid distance column, okay, we can see the distance in between Karen and Lynn, Chris, Bob, and Sam, okay? We can see that the one that is closest for Karen is Bob, okay, because it has the smallest Euclidean distance, okay? The second closest would be Sally, the third closest would be Lynn, and the fourth closest would be Chris, okay? So now then let's start thinking, or let's try to guess how much will Karen like Independence Day, given that the closest neighbor, which is Bob, ranked Independence Day with a 6, okay? So with k equals 1, we go to the closest neighbor, which is Bob, and we check the rating that Bob gave to Independence Day, which is a 6, okay? Therefore, for k equals 1, in this second little table here, we have a prediction of 6, because it's the rating that Bob gave to Independence Day, okay? We increase the complexity. We now are going to take into account 2 neighbors, okay? So we keep Bob's opinion, but now also throw in Sally's opinion, okay? Sally ranked Independence Day with a 7, okay? So now we can take the average of 7 from Sally and 6 from Bob, and the average is 6.5. So when k equals 2 with 2 neighbors, the prediction is 6.5, okay? We increase the complexity. Now we ask 3 neighbors, not only Bob and Sally, but also now Lynn will give her opinion, okay? Her opinion is that Independence Day was not good at all. She ranked it with a 2, okay? So now if we calculate the average of 7 from Sally, 6 from Bob, and 2 from Lynn, okay, we get an average of 5, okay? So as we see here, as we increase the number of neighbors, the prediction changes, okay? And this is something that for our use cases, we should always check using, for example, grid search and cross-validation in order to try out multiple values of k within all my data set in a structured way, so that we always check the predictions and the performance of the predictions in every piece of my data set, okay? And we can be sure that the value that results as the best value from grid search and cross validation is actually the best, okay? So this is how we can do it with these 2 approaches, okay? So as a summary, okay, in order to make a prediction, k nearest neighbor identifies those k training observations that are closest to the point we want to create a prediction for, okay? Then this point is assigned the class to which the plurality or the majority of observations belong. As we have seen, we can also mess with this majority by using a weighted average or a weighted voting. There are many ways to be more flexible with the opinions of the nearest neighbors, okay? So KNN is usually superior to linear discriminant analysis or logistic regressions when the decision boundary is highly nonlinear, meaning that the decision boundary cannot be separated by a line or a polynomial function, okay? But on the other hand, a KNN algorithm will not tell us anything about which predictors are important, which of the features included in the training data are important to create a prediction, okay? Because we are not ranking features, we are not ranking the variables used for training as logistic regression does with the coefficient, or as decision trees do with feature importance, okay? So KNN, it's easy to explain how it works, but it gives us very little information about which of the feature drives more the prediction, okay? Continuing the summary, okay? the model is difficult to interpret beyond the distance in between neighbors. Okay, it's super easy to say that for example, if we go back to the iPad, it's very easy to explain to your manager, for example, that we have chosen in this case, we have chosen blue as the label for this point because two of the closest points have blue versus one that has green. Okay, but beyond that, there is no more extra information or any other justification of why we chose blue versus green. Okay, so this is something that we should take into account when understanding the why the predictions are like they are. Okay, when talking about the dimensionality, when to use it, with which sizes of data and its efficiency. Okay, remember that KNN considers all predictors in the problem space, meaning that it will memorize the whole thing, the whole data frame, the whole data set. Okay, so if we are struggling with memory or with computing time, okay, what we can do is perform feature selection, okay, in order to reduce the number of features that we are including in our data set. Okay, or using our domain knowledge or our colleagues' domain knowledge, we can create new functions or for new features. Okay, that create new distance functions that are more appropriate to our specific case. Okay, so when should we use KNN? Well, it's usually not with big data, definitely. Okay, so use it when you have not too many features, less than 20 features. You need to have quite a good amount of training data. Okay, don't do it when you have let's say 25 features, 25 columns, and you have, I don't know, 100 observations, because as you increase the number of neighbors, the results are going to change dramatically. Okay, and remember that always you have to scale the values. Okay, always, absolutely always. Advantages, as we mentioned, it's very simple to use, very easy to program, to interpret, and to explain how it works. Okay, the difference here is that it's easy to interpret. Okay, it's basically distances and a voting of which value is to be chosen, but it gives us very little information about which of the feature is important to predict my class or my label. Okay, another advantage is that it can learn a quite complex decision boundary. Okay, because it will adapt to my points. Remember that it will learn everything about each point. Okay, there is no optimization phase, okay, or training required, because it will just memorize all the points. Okay, and it's only at the prediction phase when it will do calculations. Okay, so until you do like knn.predict, the computational cost is minimum. Okay, it's mostly memory cost. And the classification accuracy can be very good. Okay, it can outperform some more complex data like I don't know, linear discriminant analysis or logistic regression. Okay, because it can adjust to the decision boundary way better than those mentioned algorithms. Okay. On the other hand, the disadvantage is very slow at prediction time, at query time. Okay, and it can be easily fooled by irrelevant attributes that have the same scale of the data. Okay, if we include a variable that is that is completely made up by ourselves, okay, but has the same scale as the rest of the features, then it will be used for calculating the distance. Therefore, it can push or pull the predictions to one side or another. Okay, so always do a thorough analysis on the features, okay, and which one of them is, let's say, most correlated with the target, in order to remove the features that are just including noise and no signal. Okay, so that's our lesson about KNN. Okay, and I hope you got the gist of it and how to use it. Now you will have to work a bit on KNN yourselves with Python and the implementation of KNN made by scikit-learn. Okay, so let's do that. Thank you very much.